Hey everyone, I wanted to take this opportunity to just go over a couple of the problems from Chapter 9 and just make sure that we understand how to actually at least do the basic arithmetic operations when utilizing complex numbers within sinusoidal steady state analysis. So I'm just going to go through a couple of choice problems that we had within the homework, and hopefully if you guys had any questions over how to actually do this material, then you can easily just email me and we can actually work through that together. So we're going to start off with Chapter 9, Problem 9, and just do parts A and B. And then we're actually going to skip right over into making sure we understand how to do conversions from sine to cosine. And then from there, we're actually going to work a couple of problems and then go into Chapter 10. I'll be working on how to do source transformation within sinusoidal steady state analysis, and then basically just basic voltage division problems. We will work over how to actually do superposition in a different video. This video is mainly just to make sure you understand how to do sinusoidal steady state analysis from a base operation. So let's go ahead and just jump right into problem 9. So chapter 9, problem 9, we're going to look at basically having phi an angle of 30 degrees. And that problem was actually then multiplied by 6 minus j 8, and then plus 3 an angle of 60 degrees divided by 2 plus j. And so for this problem, when we go through, we want to take 3 an angle of 60 degrees and then divide that by 2 plus j. Now by this time, you should have been working through your Casio calculator, and you should be able to do this operation no problem. Obviously, by the arithmetic rules, if we are doing division, then we want to actually have 2 plus j in terms of its polar form, but with our calculations, we can just go ahead and punch that into our calculator and we'll get the following. So this is actually equal to phi an angle of 30 degrees, then multiplied by 6 minus j8, and then plus 1.12 plus j.74. And so from here, we can go ahead and just add the rectangular forms, and then go ahead and convert that over into its polar equivalent, and then multiply that by 5 at an angle of 30 degrees. So if we go ahead and add these together, then we get 5 at an angle of 30 degrees, and then multiplied by 7.13 plus j, 7.261. We convert that over into its polar equivalent, and that gives us the form of 10.176 at an angle of negative 45.52 degrees, and multiplied by 5 at an angle of 30 degrees. Now if we look here, it does make sense that we're going to get an angle of negative 45 degrees because the real and then imaginary portions of this number right here are actually very, very similar. So that means that we would actually have equal magnitude on the real and the imaginary axis. So when we take these two and we multiply together, obviously we multiply the magnitudes together and then add the angles. The only time when we subtract one of the angles is when we're actually doing division. So 5 multiplied by 10.176 gives us a value of 50.88, and then we add 30 degrees and negative 45.52 degrees, and that comes out to be negative 15.52 degrees. So after you go through and punch in these numbers on your calculator, especially going back and looking at 3 at an angle of 60 degrees and then 2 plus j, we should be able to get the rectangular form, convert that over, just for posterity's sake, convert that over into its polar form, and then multiply that by 5 at an angle of 30 degrees. All right, let's do part B. So that was A. For part B, we basically had a numerator multiplication and then a denominator subtraction. So here we had 10 at an angle of 60 degrees multiplied by 35 at an angle of negative 50 degrees. Then all divided by 2 plus J6 minus 5 plus J. So if we go ahead and add these two together and then multiply the top, then we actually get the following. So we get 350, again, 10 times 35, 350. We add these angles together, so that's going to be 60 minus 50 degrees. So that comes out to be 10 degrees. And within the denominator, basically 2 plus 5 and then, 2 minus 5 and then 6 minus 1j. So here we get negative 3 plus j5. We convert that into its polar equivalent. So we get 350 at an angle of 10 degrees over 5.83 at an angle of 120.96. So we divide the magnitudes, 350 divided by 5.83, and then with the angles, 10 minus 120.96. So that comes out to be equal to 60.02, an angle of negative 110.96 degrees. Okay. This is kind of weird knowing that I'm talking to a camera as opposed to talking to you guys. So I always want to turn around and ask the room if anybody has any questions, but I don't think the camera actually has any questions for me. I don't know, maybe it does. Maybe there's some really voodoo Black Mirror type of thing. All right. But if you have questions, contact me. All right. So let's now talk about what to do when we are actually considering working with sines and cosines. As I stated in class, we always want to have everything in terms of cosine, especially when we're working with multiple sources. We want to actually make sure that everything is in terms of cosine so that we appropriately compare the waveforms together. We can't compare sines and cosines because it's almost like considering comparing apples and oranges. So let's just go ahead and look at the base conversion of converting basically a time domain sinusoid into its form of basically a polar representation. Remember that we drop omega t and also cosine, and we go ahead and just leave everything in terms of the magnitude and in terms of the phase angle, because the only thing that we care about from here on out are those two, because the cosine form, the AC form, as well as that angular frequency, is present throughout the entire circuit. So this was problem 11, and we're just going to do a couple of conversions over into basically its phasor equivalent. So for part A, we're going to convert over basically V of t, which is 21 cosine for t minus 15 degrees. So V of t, and that's equal to 21 cosine for t minus 15 degrees volts. So we're just going to go ahead and convert that over. We drop the cosine, obviously we drop 4t. That's basically 4 radians per second multiplied by time. That's present in the whole entire problem. So the only thing that we care about, and just before, capital V is equal to 21, and then at an angle of negative 15 degrees. Now, how do we actually deal with converting sines to cosines? Well, we all know that cosine and sine are definitely separated by essentially 90 degrees. And dependent upon whether the sine is negative or the sine is actually positive, that determines whether we're going to add 90 degrees or subtract 90 degrees once we've converted it over into a cosine. So let's see what we do when we actually take a negative sign and convert that into a cosine. And one thing that's always good, if you ever get confused about whether you add 90 degrees or subtract 90 degrees, is take the waveform and draw it. So a negative sign, we actually can easily convert into a positive cosine simply by adding 90 degrees. So for part B, I of t is equal to negative 8 sine 10t, and then plus 70 degrees milliamps. So when we actually take this and convert that over into a cosine, when we convert that over into a cosine, the negative sign actually drops if we add on 90 degrees. So capital I is equal to positive 8 cosine of 10t. We actually have to convert into a cosine first before converting into its Phasor equivalent. So plus 70 degrees, and I'm sorry, I'm going to make sure that this is as black as possible because I hope you guys can actually see this. And then plus 90 degrees. So when we have negative sign, we want to convert that into a positive cosine, which is what we definitely want to do. Then we actually add on 90 degrees. If we have a positive sign converting that into a positive cosine, we subtract 90 degrees. Ooh, oh man, that's still I of t. So now to convert this into its Phasor equivalent, capital I is equal to 8, and then we just add 70 and 90 together, and that is positive 160 degrees milliamps. Okay, positive 160 degrees. So let's take a look at what we do when we just have that positive sign converting into a cosine. Like I said here, with negative sign, we added 90 degrees. Now we're actually going to subtract off 90 degrees when we go from positive sign to a positive cosine. So for part C, here we have V of t. That is equal to 120 sine, and then 10t minus 50 degrees volts. So for here, we just want to convert that easily into a cosine by subtracting off 90 degrees. So that will give us negative 50 minus 90 degrees. That gives us negative 140 degrees. So that's equal to 120 cosine 10t minus 50 degrees minus 90 degrees volts. So that comes into negative 140 for here. So capital V is equal to 120 and an angle of negative 140 degrees volts. And guys, remember the reason why we want to convert sine into cosine, you will see this on the test. Sine to cosine is because we have to compare a cosine to a cosine. If we're looking at just sine waves, which is generally not the convention that we work with in this class, then we are actually comparing sines to sines. But in order to actually make our calculations appropriate, we want to make sure that everything is all in terms of cosine, all in terms of sine. Now, for this class, like I said, I want everything in terms of cosine. All right. So these couple of problems should have been good review for you guys, just to make sure you understand actually how to do the arithmetic calculations. In problem 13, parts A and B, those essentially are the same calculations, same thing in 17. If you have any questions on 13 and 17, make sure that you contact me so that we can actually figure this thing out and that you are on track. So let's do problem 35. Let's go ahead and look through how to actually, just as a review again, this should have been more of a review from what we've done in class, on how to actually take the schematic. We're going to convert that into, basically for the inductor and the capacitor, their impedance equivalents, and then, as always, all we have to do is just apply all of the concepts that we worked on in chapters 2, 3, and 4. The whole entire circuit, basically, with sinusoidal steady state analysis, just becomes like solving everything with DC. But this time, because we're not concerned about that transient period, we're only concerned about how the system functions when it's in a sinusoidal steady state. So let's take a look here. Now, problem 35, or just simple series circuit. This should have been super easy for you guys. Let's see if I can switch to a pen that actually is a little more visible. So for 35, we're going to find IFT. We're going to find the source current. So find IFT. So here we have AC source. This is horrid. Maybe a little bit better. So here we have 50 cosine of 200t. We have 10 ohm resistor, 5 millifarad capacitor, and then in series with a 20 millihenry inductor. So all we have to do is convert everything over first into basically their impedance equivalents. And so don't forget that for the impedance, for the inductor, ZL, that's just equal to J omega L. So J omega L. So we take omega from basically cosine waveform, which was 200 radians per second, and we multiply that by 20 millihenries. Milli is obviously 10 to the negative third. So here we get J 200, and then multiply that by 20 times 10 to the negative third, and that value comes out to be equal to J 4 ohms. Remember the units for any impedance is ohms, because this is what we're doing to ensure that we can actually perform these analysis techniques as if everything was DC. But we replace basically the AC and we utilize the complex number. Now for ZC, that's 1 over J omega C. 1 over J omega C, so obviously J becomes equal, 1 over J becomes equal to negative J divided by omega C. So negative J over 200 times 5 times 10 to the negative third, and that comes out to be equal to negative J ohms. All right. So once we've actually converted everything over, then we can easily just go ahead and start applying DC techniques. So here's ZL, we can just replace that with J 4. For here we have negative J for a capacitor. Always note that the impedance for a capacitor is always going to be negative, and that for the inductor will always be positive. Over here, there's no phase angle, so 50 cosine 200t. So that's just going to be equal to 50 and an angle of 0 degrees. So for now, we can actually go through and just apply KVL in order to actually find I. So very simply, instead of having Ohm's law now, we have V is equal to IZ. And so we can go ahead, look at the total impedance, or the equivalent impedance actually seen by that source. And so for here, we have I, and then we go ahead around the closed loop, apply KVL just like we did before. So 10 minus J, and then plus J4, and that would actually be equal to 50 and an angle of 0 degrees. So I is therefore equal to 50 and an angle of 0 degrees over 10 plus J3. And so from here we just basically convert that into, well, we just punch it into the calculator, or we convert that into essentially its polar equivalent. So 50, an angle of 0 degrees over 10.44, an angle of 16.7 degrees. And then from here, we actually calculate that I comes out to be equal to 4.789, an angle of negative 16.7 degrees amps. And that's the current that we actually get from here, especially if I go through and make sure the 4 actually looks like a 4. But guys, remember, all the phasor techniques do for us is actually give us a tool to go through and find that sinusoidal steady state form here. But obviously we can always go back and answer the question, what does the current actually look like within the circuit? But we're concerned always with the time domain, always with the time domain. So go back and reconvert that I of t by this magnitude here, 4.789. So 4.789 times cosine, and then 200t minus 16.7 degrees amps. And this is the true answer that we're really concerned with when it comes to actually looking at the current within the circuit. Okay.